So we got the characteristic equation of a second order system as this: s square plus 2 zeta omega ns plus omega n square. Now if we compare it to the standard representation of a quadratic equation, that is ax square plus bx plus c, we can see that here a is equal to 1, b is equal to 2 zeta omega n, and c is equal to omega n square. Okay, so if we try to find the roots of this characteristic equation, okay, the roots, so this will be, the roots will be s is equal to minus b plus minus b square minus 4ac by 2a. Okay, this is the formula. So this will become minus 2 zeta omega n plus minus 4 zeta square omega n square minus 4ac, 4 omega n square, by 2 into 1, that is simply 2. Okay, so this will be the roots of the characteristic equation. Now here different cases arise for different values of zeta. Okay, so let us just further simplify it. This will become minus zeta omega n plus minus, the 4 will come out in the form of 2 into omega n square into sigma square, zeta square minus 1 by 2. Okay, so here 2 will get cancelled out from both the numerator and the denominator, and this will become minus zeta omega n plus minus omega n to root over of zeta square minus 1. Okay, so this will be the expression, the roots s1 and 2. There will be two roots. So this is the expression. So we got the roots of the characteristic equation of a second order system in the form of this: minus zeta omega n plus minus omega n into root over of zeta square minus 1. So we can further write it as the first root. Let's say we take it as minus zeta omega n minus omega n to root over of zeta square minus 1, and the second root, let's say it is minus zeta omega n plus omega n into root over of zeta square minus 1. Okay, so now for different values of zeta, which is the damping ratio, the location of the roots will change. So there will be 4 cases arising here. Okay, 4 cases. First one is when this zeta will be greater than 1, which will be called as the overdamped case. The second will be when zeta will be lesser than 1, which will be the underdamped case. The third one will be when zeta will be equal to 1. This will be the critically damped case. Okay, critically damped. And the fourth one will be when zeta will be 0, no damping. So that will be called as the undamped case. So we'll analyze the behavior of these roots for these 4 cases one by one. Okay. So let us consider the first case in which zeta is greater than 1, which is the overdamped case. So here the value of S1 and S2 will stay the same. That is, S1 will be equal to minus zeta omega n minus omega n into root over of zeta square minus 1, and S2 will be minus zeta omega n plus omega n into root over of zeta square minus 1. Okay, because zeta is a 1, greater than 1. So when zeta will be greater than 1, obviously zeta square will also be greater than 1. So there will be no imaginary roots here. That is the most important thing. So both of them, the roots will be real and negative. Both the roots will be real and negative. No complex roots, no imaginary values, because zeta is greater than 1. When zeta will be greater than 1, zeta square will also be greater than 1. So obviously there will no imaginary term coming here. No complex roots. Both the roots will be real and negative, and if we plot those roots on the complex plane, it will be like this. Okay, sigma j omega. Okay, so obviously the S1 will have a higher negative magnitude and S2 have a lower magnitude. See, it will be closer to the origin S2 because of this plus term, and here both of the terms have negative signs, so it will be a little farther away from the origin. It will be more negative. S1 will be more negative than S2. Okay, so this is for the overdamped case. Okay, so the second case is when zeta is equal to 1, that is the critically damped case. So in this case, if we substitute the value of zeta with 1, S1 will become minus omega n to root over of 1 minus 1. Obviously this will become 0, and S2 will also be minus omega n plus omega n into root over of 1 minus 1. This will also become 0. So both S1 is equal to S2 is equal to minus omega n. Okay, so both of the roots are equal. Okay, both the roots are negative and equal. So if we plot the roots, okay, on the complex plane, sigma j omega, the location of the roots will be the same. Both S1 and S2 are located at the same point, okay, equals to minus omega n. So this is for the critically damped case where zeta is equal to 1. So now let us consider the third case, which is the underdamped case where zeta is lesser than 1. Okay, so when zeta will be lesser than 1, so please focus at this portion only. Then we'll go for the remaining omega n into root over of zeta square minus 1. For now, just focus on this portion. So when zeta will be less than 1, obviously there will be a negative term coming under this root, okay, this under root. So we can write it as minus 1 minus zeta square, okay. So this will become plus minus j omega n into root over of 1 minus zeta square, okay. Please understand, zeta is lesser than 1, so zeta square minus 1, it will come in a negative form because zeta is lesser than 1, so zeta square will also be lesser than 1. So this will come in the form of a negative number. So we can write it as minus 1 minus zeta square. So we know that the root over of minus 1 is iota or j, whatever in the imaginary notation. So we can write it in the form of this. Now let us just put these values just before it, okay, minus zeta omega n, okay, minus zeta omega n. This will remain as it is regardless of the value that zeta is lesser than 1. This will remain as it is. So this will be the root of the characteristic equation for a second order system for the underdamped case. So here we are getting complex roots, okay, complex roots with negative real parts, okay, complex roots with negative real parts, and the imaginary parts are mirror images, okay, the imaginary parts are mirror images of each other. So if we plot this the roots on the complex plane, it will be something like this, okay. This will be minus zeta omega n, okay, so this will be minus j omega n to root over of 1 minus sigma square, and this will be plus j omega n into root over of 1 minus sigma square. So let us just call this as S1 and this as S2, okay. So this is the location or plot of the roots for the underdamped case when zeta is lesser than 1. This is S1, this is S2. Now the only case which is remaining is the undamped case where zeta is equal to 0. Okay, let us discuss that as well. So let us discuss the fourth and final case, which is zeta is equal to 0 or the undamped case. So when zeta becomes 0, so obviously S1 and S2, okay, S2 will be minus 0 minus omega n into root over of minus 1 and minus 0 plus omega n into root over of minus 1 because zeta is 0. So we can write it as plus minus j omega n, because we know that root over of minus 1 is equal to j. So this is the location of or the roots for an undamped second order system. Okay, plus minus j omega n. So we can say S1, let's say it is plus j omega n, and S2 is equal to minus j omega n. So they will lie on the imaginary axis. Okay, so if we try to plot the roots, it will be simply be located on the imaginary axis as mirror images. Let's say this one is plus j omega n, and this is S2 is equal to minus j omega n. Okay, so this is about the undamped case of a second order system. So here we have discussed the 4 cases or the damping cases, that is overdamped, underdamped, critically damped and undamped for a second order system, and we studied the nature of the roots for these 4 cases. Okay, so we discussed about the basic concept or the forward and feedback transfer functions of a second order system, and the concept of natural frequency, undamped natural frequency, damping ratio, and the 4 cases of damping. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.